Hello everyone, my name is Kan Yu. I'm glad to present this paper on behalf of all the authors. This is a joint work with Dr. Fang, Dr. Gui, Dr. Feng, and Dr. Hu. Nowadays, the dynamic bipartite graph serves as a basis for many important tasks, such as e-commerce and online education. In e-commerce, users and the products are the two sets of nodes, and an edge represents a user purchased a product. It is a critical task to detect anomalies to strengthen protection against attacks, especially on dynamic graphs. For instance, in the example of e-commerce, we would like to know whether this transaction a payment fraud. In the MOOC platform, students can take actions regarding to courses. We would like to know whether the students will drop a course after this action. The running theme of the two previous examples is that given the dynamic bipartite graph, we aim to determine whether a recent edge is anomalous. So in this paper, a dynamic bipartite graph is formed by a sequence of temporal interactions, where each interaction represents a source node U interacts with a destination node V at a timestamp t. Given a dynamic bipartite graph, the inductive anomaly detection problem aims to train an anomaly detection model such that when a new edge arrives, the model can determine whether this edge is anomalous. Please note that we are talking about inductive setting, which means the node U may not be seen in the training data. There are three challenges for this problem. The first one is the inductive setting. It means the proposed solution should be capable of generalizing to new unseen data. The second challenge is the limited or even no attribute on nodes in the graph, which is quite common in practice. So we need to utilize the structural information. The third challenge is the lack of explicit definition of anomaly. It means we need to learn from the data. By reviewing the existing methods, we notice that methods like MIDAS and IFIT, they detect predefined anomalies and they require the node has attributes. For JN-based methods, because they need to aggregate node or edge features, so their performance is not satisfying when the graph has no edge or node attributes. For graph embedding methods, they assign a learnable vector for each node in the graph. So they cannot handle the inductive setting because when a single node comes, they have to retrain their model to get the reputation for the node, which is extremely expensive. For IGRL and GraphSage, these methods work on static graphs, so they cannot capture temporal information. CW is an inductive graph representation method, and it is more similar to our proposed solution. So in the experiments, we will show that our proposed solution outperforms CW in the anomaly detection task because this one is a general method. It's not designed for anomaly detection. So how to detect anomalies inductively? In order to predict whether a target edge UVT is anomalous, the outline is quite straightforward. So first, we collect edge UVT and the edges from U before time t, and then we encode all the collected edges. Finally, we will pass the representation to a model to make the prediction. So this outline raises two questions. The first one is how to represent an edge, and the second one is how to predict. In the following, we will elaborate on the two questions in turn. So for the first question, before we design a solution, we would like to know what a good edge representation looks like. So ideally, the representation can be computed based on the structure without using the node identity information. We cannot assign learnable vectors for the nodes. So this secondly, it does not rely on node attributes. And thirdly, it should preserve sufficient information for anomaly detection. And also, it should be fast because this is we are processing dynamic bipartite graphs, and we would like to the model has a high throughput. So the first 3 points corresponds to the 3 challenges respectively. A natural idea for this is as follows. So first, we extract edge features based on the structure. Next, we train an encoder to encode the features into an anomaly-aware representation. So what features should we extract first? A naive idea is we can use node centrality or edge centrality or other measures like degree, betweenness, clustering coefficient. Assume we want to extract features for edge UV. We can compute the degree for node U and node V respectively, which is 3 and 3. And we can make the feature vector as 3, 3. Even though this is quite easy to implement, the extracted features have nothing to do with anomaly. Intuitively, an edge is anomalous if its pattern significantly deviates from the normal patterns. So we would like to extract features that can capture this kind of differences. We know that in the bipartite graphs, the source node and the destination node play different roles, so they should be treated differently. It means we should extract features from source node's perspective and extract features from destination node's perspective, respectively. So on the source node side, we observe that source nodes sharing common neighbors are expected to exhibit similar behaviors. So in this example, we notice that U, U1, and U2, all of them have visited destination node V. So U, U1, and U2 are expected to exhibit similar behaviors. We call U1 and U2 the partners of U. Here, the behaviors can be the sequence of destination nodes that the source node have interacted with. So this implies that the similarity between the interaction history of U and U1 and U and U2 is useful for anomaly detection. But the question is how to capture the similarity. So a naive idea is to use the Jacquard similarity between the interaction histories. However, this idea failed to capture the similarity between destination nodes. So we consider two interaction histories. One is iPhone 14 and AirPods. The other one is iPad and AirPods Pro. We can see the two interaction histories are totally different, but they are highly correlated. So to tackle this issue, in our solution, we propose an alias-based method. So assume we want to extract features for edge UV, and we will make V the pivot node. The alias of each destination node is the similarity between V and Vi. So with this alias defined, the interaction history of U1 is encoded as this. So each destination node is replaced by its alias. So for each partner, we can get this vector, feature vector, and the features from the source node's perspective is the collection of all these vectors. For the destination node side, we observe that the associations between V and other destination nodes that View has visited before implies the dynamic rule of how the graph evolves. For instance, many people will buy a phone case after they have bought a phone. In this example, we know that source node U have interacted with destination node V, V1, and V2. So we can make two association pairs VV1 and VV2. We would like to know, do other source nodes also interact with V1 before V and V2 before V? So this question implies the popularity of association pairs is useful for anomaly detection. So the question is how to define the popularity. The naive idea to capture the popularity is as follows. For each association pair VVI, we collect the set of source nodes that have this pair in their interaction history. So in this example, there are two pairs in use interaction history, which is VV1 and VV2. We know VV1 appears in the interaction history of U and U2. VV2 appears in the interaction history of U and U1. So the feature vector is 2, 2. This idea has one drawback. It treats all the source nodes equally and disregards the differences. I will use an example to explain this. So consider this example. There are 3 users, computer scientist, software engineer, and a student, and they buy laptop, keyboard, and football. Assume we want to extract features for the edge between computer scientist and the laptop. So there are 2 association pairs, laptop keyboard and the laptop football. We see laptop keyboard appears in the interact history of software engineer, and the laptop football appears in the interact history of student. If we only use the number of source nodes that contain this pair, the popularity score of these 2 pairs are both 1. But because we know software engineer is more similar to computer scientist, so this pair should be more important. So to tackle this issue in our solution, for each association pair, we collect the set of source nodes whose interaction history contains this pair. Then we compute the similarity between U and U prime for every U prime in the set. And we will draw a histogram to represent the distribution of similarity score. The histogram corresponds to the feature vector for the pair. In this example, we can compute the similarity between UU1, UU2, and UU3 as this. And for the 2 pairs, we can collect the set of source nodes that contain these pairs. And the corresponding histogram is like this. So in summary, to extract features for edge UVT, from the source node side, we generate a feature vector for every partner. And from the destination node side, we generate a feature vector for each association pair. Next, we use an encoder to encode the features into representations. Because we have the feature vectors for the partners and the association pairs, we observe that not all partners or the association pairs should be used to generate edge representations. Here is an example. Assume a computer scientist just starts hacking. He may buy the same hacking stick as a hacking enthusiastic. So is the hacking enthusiastic a good partner? We don't think so, because they don't have much in common. And he may buy the graphic card before he buys the hacking stick. Is graphic card hacking stick a good association pair? We also don't think so, because in real life, these 2 items are unlikely to be linked. So this example tells us we shouldn't use all partners and association pairs to generate edge representations. Therefore, we design partner mask and association mask to select the appropriate partners and association pairs. So here, assume we use S partner masks and D association masks. So each mask will select a set of appropriate partners and association pairs, and the selected feature vectors will be passed to encoders. The output of this encoder will then further passed into a neural network to generate the final representations. And each representation corresponds to a specific association mask and partner mask. Because we have S partner masks and D association masks, we have S times D anonymous edge representations. Next, we answer how to make the prediction. Because we have encoded all the collected edges, we have the edge UVT, we have the sequence of edges from U at and before time t. So we will pass the repetition of this sequence to a model to make the prediction. Because we have S times D repetition for each edge, and so we have S times D sequences. Each sequence will be passed into a sequence encoder, and to compute the anomaly score, we will compute take the maximum score as the final prediction score. In our experimental study, we use 3 datasets with real anomalies and 2 datasets with synthetic anomalies. We compare our methods with 9 state-of-the-art methods, including 2 anomaly detection methods that propose to detect predefined anomalies, and 2 representation-based anomaly detection methods and 4 inductive graph representation methods. In this from this table, we can see that the proposed methods achieves the best performance. We also conduct an evaluation study to evaluate the effectiveness of each component in our solution. And we report the prediction accuracy by varying the hyperparameters. We also report the throughput of the proposed model.